Hello there and welcome back. We're continuing where we left off with our problems by looking at our second example here, where we are going to try to show that n3 times n squared plus n is going to be in the set of big O of n squared. So let's pick this up, move it over here and take a look at this. And so just like I said, I'm going to start each of these videos by reminding ourselves of what that definition of big O is, because we're going to need that to be able to do our proof. So by definition, a function f of n will be inside big O of g of n, inside that set, if and only if there exists an m greater than 0 and there exists an n naught greater than 0 for all n greater than n naught, such that f of n is less than or equal to m times g of n. And so holding on to that, what we're going to say is, what was our original problem? So 3n squared plus n will be in here if and only if there exists an m greater than 0 and an n naught greater than 0 for all n greater than n naught, where 3n squared plus n is less than or equal to m times n squared. There we go. So now we have this problem space, just as we would want there to be. And we're going to first do a little bit of scrap work to determine what we need to solve this problem. And then once we finish with our scrap work, we can we can go ahead and go and write like our more formal proof, we'll say, right? Walking it back from that point. Okay, so just like our previous example, we're going to want to try and do our round up. So I look at this problem space here and I can see that we've got an n squared over here, we've got an n squared over here. We're trying to get a form where we end up with something times n squared, but we have this pesky extra thing here, and it sure would be nice to wrap this up into there. So if I can pick an n naught value that will make sure that n is, pick an n naught value. I'm going to write this in not red since it's not part of the official proof. Pick an n naught value such that we can say n is always going to be less than, or I guess, or equal to n squared. So if we say it's less than, n is always less than n squared, we can also just widen that condition and say less than or equal to n squared. So we want to pick an n naught value where this will be true so that we can use that round up trick. And so typically, as long as we're picking an n naught value that pushes us into the integer, positive integers, I guess I should say non-negative integer, no, positive integers, we don't want to include 0, we're usually pretty well off. So let's switch back. Let's actually stay in our scrap work for a second, and let's pick that our n naught should be 1, so that our n should be greater than 1. Now, keeping that in mind, we know that that means that 1 is less than n, which will be less than n squared, which will be less than n cubed, and so on and so forth. So we can make sure that 3n squared plus n is going to be less than or equal to 3n squared plus n squared, which we know is the same as 4n squared. And now we're finally going to be in that format that matches what we were looking for. So armed with this information, we can finish off our real proof. All we've done so far is define our problem space. We can say let m equal 4 and n naught equal 1. We will show for all n greater than 1 that n, what is it, 3n squared? Is that right? Yep, 3n squared plus n is less than or equal to n squared. All right, so what we can do here is we can take those two values, and did I write that right? 3n squared plus n is less than or equal to m times n squared. I always forget that m. All right, so we can sub in the values that we just said we definitely knew that we had. Since n is greater than 1, 3n squared plus n is going to definitely be less than 3n squared plus n squared, which is the same as 4n squared. 4n squared less than or equal to m times n squared. Put m equals 4 in, and we'll see that we get 4n squared less than or equal to 4n squared, which proves exactly what we were looking for right there. So therefore, 3n squared plus n is definitely going to be big O n squared. And we can actually see why, right? So we can use this round up trick to basically show that we're, even if that plus n got bigger, which it's not, we would still be in that m times n squared problem space. Okay, we're gonna do another example in a different video where we're gonna switch it up a little bit. We're gonna switch from our rounding up trick and that big O to look at big omega instead. Big O is usually pretty straightforward for us since it is gonna be a worst case. Actually, I will just say one more thing about that. So just as a reminder that when we're talking big O, we are talking about a worst case. So we're looking for an upper bound, which is that m times g of n for our function. So basically, when we're talking about big O, it makes a lot of sense to be talking about this round up trick because we want to show that even when we round up and we end up a little bit higher up in this graph and we round our value up in whatever way, we still stay underneath that bound or at that bound. So that makes a lot of sense that big O may use round up. Right? Nothing is like 100% always all the time, but it makes sense. It's a really good starting place to look at these round up style questions. Okay, so that is our second exercise. And after that, we are going to take a look at the big omega factoring out tricks. Thanks, and I'll see you there.